Listen closely. Albert Einstein was born on March 14, 1879, in the small town of Ulm, in the Kingdom of Württemberg, part of the German Empire. He was the first child of Hermann Einstein, a salesman, and Pauline Koch, a homemaker. His family moved to Munich shortly after his birth, where his father and uncle ran an electrical engineering company. Yalla. Despite his early speech delays, which led some to worry about his intellectual development, Einstein displayed a remarkable curiosity about the world. He was particularly drawn to mathematics and science, even from a young age, showing a deep interest in geometry and how the world functioned around him. After completing his primary education in Munich, Einstein faced challenges in the traditional educational system, particularly with the strict, authoritarian style of teaching. His rebellious nature and unconventional thinking led him to leave Germany for Switzerland in his late teens. He enrolled at the Swiss Federal Polytechnic in Zurich in 1896 to pursue a degree in teaching, which allowed him to further immerse himself in physics and mathematics. Einstein graduated in 1900 and initially struggled to find a teaching position. He eventually found work at the Swiss Patent Office in Bern, which provided him with ample time to focus on his own research and ideas about the fundamental nature of the universe. During his years working at the Patent Office, Einstein produced some of the most revolutionary work in the history of science. In 1905, a year often referred to as his Annus Mirabilis, or miracle year, he published 4 groundbreaking papers in the journal Annalen der Physik. These papers covered topics ranging from the nature of light to the behavior of particles, but the most famous one introduced the special theory of relativity. This work fundamentally altered the way we understand space, time, and the relationship between energy and matter. His equation, E equals mc2, became 1 in 1915. Einstein expanded his theories with the general theory of relativity, which introduced a new understanding of gravity. His work showed that gravity was not a force acting at a distance, as had been previously thought, but a curvature in space-time caused by massive objects. The theory was confirmed in 1919 when British astronomers observed the bending of light around the sun during a solar eclipse, providing experimental evidence for Einstein's predictions. This confirmation catapulted him into global fame. In 1921, Einstein was awarded the Nobel Prize in Physics, but it was for his explanation of the photoelectric effect, rather than for his work on relativity. This recognition helped cement his place as one of the most influential scientists of his time. However, his growing prominence also made him a target for political and ideological opposition, especially as the Nazi Party rose to power in Germany. Fearing for his safety due to the regime's increasing anti-Semitism, Einstein emigrated to the United States in 1933. Where he accepted a position at the Institute for Advanced Study in Princeton, New Jersey. He became a U.S. citizen in 1940 and continued his work in both theoretical physics and political activism. Although he was known for his pacifist views, Einstein played a crucial role in alerting President Franklin D. Roosevelt to the potential of nuclear weapons, leading to the establishment of the Manhattan Project. Einstein spent the later years of his life working on a unified field theory, attempting to reconcile the forces of gravity and electromagnetism. Though he was never able to complete this work, he died on April 18, 1955, at the age of 76. In Princeton. His passing marked the end of an era in physics, but his contributions have left an indelible mark on both science and the world, continuing to inspire new generations of thinkers and researchers. His name remains synonymous with genius, and his theories continue to shape our understanding of the cosmos. After graduating from the Polytechnic Institute in Zurich in 1000, 900, Einstein faced difficulty finding a permanent academic position. Despite his academic success, he struggled to secure a teaching job due to his unconventional thinking and his preference for independent work. In the meantime, he supported himself by working as a tutor and even briefly as a school teacher. But it was his employment at the Swiss Patent Office in Bern that proved to be a turning point. In 1902, he began working as a technical examiner, reviewing patent applications for inventions related to electromagnetic devices. At the Patent Office, Einstein's work involved evaluating the technical details of inventions, which required him to assess complex concepts in physics and engineering. This job allowed him the flexibility to dedicate time to his own studies and research. With the knowledge he gained from reviewing patents and his growing dissatisfaction with conventional physics, Einstein began exploring groundbreaking ideas in the field of theoretical physics. While working at the Patent Office, he managed to write and publish several important papers that would later define his legacy. One of his most well-known works came in 1905, often referred to as Einstein's Annus Mirabilis, or Miracle Year, when he published 4 papers in the scientific journal Annalen der Physik. These papers covered a range of topics, including the nature of light, Brownian motion, and the photoelectric effect. His paper on the photoelectric effect was particularly notable because it provided experimental evidence for Max Planck's quantum theory of light. This was a major breakthrough, showing that light could be understood as both a wave and a particle. Einstein's work in this area not only earned him the Nobel Prize in Physics in 1921, but it also laid the foundation for much of modern quantum mechanics. Another paper published in 1905 introduced his special theory of relativity, which was revolutionary in its approach to space, time, and the speed of light. Einstein argued that the laws of physics are the same for all observers, regardless of their motion, and that the speed of light is constant for all observers. His famous equation, E equals mc2, which expresses the equivalence of mass and energy, came from this theory. This equation has become one of the most famous in all of science, demonstrating the immense energy that could be released from even a small amount of mass. Following the success of his 1905 papers, Einstein's reputation as a physicist began to grow. In 1909, he was appointed a full professor at the University of Zurich. And a few years later, in 1914, he moved to Berlin to join the Prussian Academy of Sciences. There, he continued to refine his ideas, developing the general theory of relativity, a theory that expanded upon his earlier work on special relativity. The general theory of relativity, published in 1915, explained gravity as the curvature of space-time caused by massive objects, revolutionizing our understanding of gravity, which had been based on Newtonian physics for centuries. Einstein's work on general relativity gained worldwide attention, and in 1919, when British astronomers led by Sir Arthur Eddington observed the bending of light from distant stars as it passed near the sun during a solar eclipse, the theory was confirmed. This validation of Einstein's predictions led to his international fame, and he became a global icon, celebrated not only as a scientist, but also as a symbol of intellectual achievement and progress. Despite his fame, Einstein's later years in Europe were overshadowed by the rise of Nazism in Germany. As a Jewish intellectual, Einstein was increasingly targeted by the Nazi regime. In 1933, when Adolf Hitler came to power, Einstein was visiting the United States and decided not to return to Germany. He took up a position at the Institute for Advanced Study in Princeton, New Jersey, where he would spend the rest of his career. In the U.S., Einstein became deeply involved in politics, advocating for pacifism, civil rights, and the eventual establishment of a world government to prevent war. During World War II, Einstein was initially a vocal advocate for peace and was concerned about the potential for nuclear weapons. However, when he learned that Nazi scientists were conducting research on atomic bombs, he co-signed a letter to President Franklin D. Roosevelt in 1939, urging the U.S. government to begin its own atomic bomb research. This letter led to the creation of the Manhattan Project, although Einstein himself was not directly involved in the project. His later years in America saw him become a prominent figure in the campaign for civil rights, speaking out against racial segregation and discrimination, particularly in relation to African Americans. Throughout the later part of his life, Einstein continued to search for a unified theory of the forces of nature, trying to reconcile general relativity with quantum mechanics. This work, known as the unified field theory, occupied much of his energy, but he was never able to complete it before his death. In his personal life, Einstein had 2 marriages. First to Mileva Maric, with whom he had 2 sons, and later to his cousin Elsa Lowenthal. He also enjoyed music, playing the violin throughout his life. Einstein died on April 18, 1955, at the age of 76 from an abdominal aneurysm. His passing marked the end of an era in physics, but his contributions to science and humanity continue to shape the world today. His groundbreaking theories not only revolutionized the field of physics, but also laid the groundwork for many modern technologies, including GPS systems and nuclear energy. His name remains synonymous with brilliance, and his legacy as one of the most influential scientists in history endures. Einstein's special theory of relativity, published in 1905, radically transformed our understanding of space, time, and the nature of the universe. Before Einstein, the accepted view of space and time was largely based on Isaac Newton's classical mechanics, which treated space and time as fixed and absolute entities. Newton believed that time passed the same for everyone and that space was a static, unchanging backdrop. However, Einstein's special theory of relativity turned this conventional wisdom on its head. The key idea behind special relativity is that the laws of physics are the same for all observers, no matter how fast they are moving, as long as they are not accelerating. This principle is called the principle of relativity. Einstein showed that in this framework, space and time are not independent and absolute quantities, but are linked together as space-time. More importantly, he proposed that the speed of light in a vacuum is constant and always the same, regardless of the motion of the light source or the observer. This idea was a dramatic departure from classical physics, where speeds were considered relative to the observer. One of the most profound consequences of the special theory of relativity was the realization that space and time are not fixed and independent. Instead, they are interconnected and can stretch or shrink depending on the relative motion of the observer. This led to the concept of time dilation, the idea that time passes more slowly for objects that are moving close to the speed of light. For instance, a person traveling in a spaceship at near light speed would experience time much more slowly than someone remaining on Earth. Similarly, objects moving at high speeds experience length contraction, meaning that they shrink in the direction of motion when observed from a stationary point of view. One of the most famous and widely recognized outcomes of Einstein's theory was his equation E equals mc2. This equation shows the equivalence between mass and energy. In simple terms, it suggests that energy and mass are 2 forms of the same thing, and that a small amount of mass can be converted into a tremendous amount of energy. This relationship explained why nuclear reactions, such as those in the sun or nuclear power plants, release so much energy from such small amounts of matter. Then the simple suggestion is that if the diorama is only in nuclear reactions, the mass cannot be converted into a small amount of matter. The equation E=mc2 also became a central tenet of Einstein's work, playing a critical role in both theoretical physics and practical applications such as the development of nuclear energy and weapons. Einstein's special theory of relativity not only reshaped our understanding of space and time, but also laid the foundation for many. His work paved the way for the development of quantum mechanics, which explains the behavior of particles at atomic and subatomic levels. Additionally, the theory has practical applications in modern technologies. For instance, the Global Positioning System, GPS, which relies on satellites orbiting the Earth, must account for time dilation effects predicted by special relativity to provide accurate location data. The clocks on the satellites tick slightly faster than those on the ground due to their high speed and weaker gravity, and without this correction, the system would be off by kilometers. Einstein didn't stop with the special theory of relativity. In 1915, he expanded his ideas further, developing the general theory of relativity, which provided an entirely new perspective on gravity. Prior to Einstein, gravity was understood through Newton's law of universal gravitation, which described gravity as a force acting at a distance between two objects with mass. However, Einstein's theory showed that gravity is not a force in the traditional sense, but rather a result of the curvature of space-time caused by the presence of mass and energy. In general relativity, Einstein proposed that massive objects, like the Earth or the Sun, warp the fabric of space-time around them. This warping causes smaller objects, like planets or light, to follow curved paths. For example, the Earth orbits the Sun, not because the Sun exerts an invisible force on the Earth, as Newton suggested, but because the Sun's mass has caused a depression in space-time, and the Earth is simply following the curved path within this warped space-time. This is often referred to as the curvature of space-time. One of the key predictions of general relativity was that light should bend when it passes near a massive object, like the sun. This was a bold and counterintuitive idea because, at the time, light was considered to be purely a wave. In 1919, during a solar eclipse, a team of British astronomers led by Sir Arthur Eddington confirmed this prediction by observing the bending of starlight around the sun. This was one of the first experimental validations of general relativity and helped cement Einstein's status as a scientific revolutionary. General relativity also predicted the existence of black holes, regions of space where the gravitational pull is so strong that nothing, not even light, can escape. Although the concept of black holes was not fully understood or accepted in Einstein's time, the theory provided the framework for later discoveries in astrophysics, including the observation of black holes and the study of phenomena like gravitational waves, which were first detected in 2015. Einstein's contributions to physics are not limited to his theories of relativity. He also made significant contributions to the development of quantum mechanics, although he famously had reservations about some aspects of the theory. One of his early contributions was the explanation of the photoelectric effect in 1905, which demonstrated that light can behave as discrete particles, later called photons, and not just waves. This was a crucial step in the development of quantum theory and earned him the Nobel Prize in Physics in 1921. However, Einstein was skeptical of the idea that quantum mechanics could be a complete description of the universe, famously stating, "God does not play dice with the universe." Despite this, his work on the quantum nature of light had a profound impact on the development of quantum mechanics and its applications in technologies like lasers and semiconductors. Einstein's ideas about relativity not only reshaped the field of physics, but also deeply influenced other areas of science and philosophy. His work prompted new ways of thinking about space, time, and the nature of reality, inspiring a generation of physicists to push the boundaries of scientific knowledge. In 1921, Albert Einstein was awarded the Nobel Prize in Physics, though it wasn't for his groundbreaking work on relativity, as many people assume. Instead, he received the prestigious honor for his explanation of the photoelectric effect, a phenomenon that had puzzled physicists for years. The photoelectric effect refers to the process by which electrons are ejected from a material when light shines on it. Classical physics had trouble explaining why certain metals only emitted electrons when the light was of a specific frequency, regardless of its intensity. Einstein's work on the photoelectric effect was pivotal because he proposed that light is not just a continuous wave but also consists of discrete packets of energy, which he called quanta. This particle-like nature of light, later known as photons, helped explain the photoelectric effect. His work provided crucial evidence for Max Planck's theory of quantum mechanics, which proposed that energy is quantized. Einstein's insight into the dual nature of light, both as a wave and as particles, contributed significantly to the foundation of quantum theory, a field that would later become one of the most important areas of physics. The Nobel Prize recognition in 1921 was not just a personal triumph for Einstein, but also a turning point for the broader scientific community. While relativity was starting to gain attention, the photoelectric effect was a more tangible, experimentally verifiable breakthrough that could be understood within the classical physics framework. It gave Einstein international acclaim and cemented his reputation as one of the most important physicists of his time. However, despite his Nobel recognition, Einstein remained deeply concerned with the philosophical implications of his work, particularly in relation to quantum mechanics, with which he would engage in intense debate for the rest of his life. Though the Nobel Prize acknowledged Einstein's contributions to quantum theory, Einstein himself was never fully comfortable with the idea that nature operated in an inherently probabilistic manner, as quantum mechanics suggested. One of the most famous quotes associated with Einstein is, "God does not play dice with the universe." He was not fully convinced that quantum mechanics, with its inherent uncertainty and probabilistic predictions, was the final description of reality. His philosophical objections to the theory led to one of the most famous debates in physics, where he squared off against Niels Bohr, one of the leading proponents of quantum mechanics. Their debates, known as the Bohr-Weinstein debates, centered on the interpretation of quantum mechanics and the nature of reality. Einstein believed in an orderly, deterministic universe, governed by natural laws that could in theory be fully understood and predicted. On the other hand, Bohr argued that quantum mechanics, with its uncertainties and probabilistic nature, was the most accurate description of nature, even if it defied human intuition. Einstein's skepticism about quantum mechanics led to several thought experiments, including his famous EPR paradox, Einstein-Podolsky-Rosen paradox, which questioned whether quantum mechanics could provide a complete description of physical reality. While the debate did not lead to a resolution during their lifetimes, it shaped the development of quantum theory and pushed the scientific community to delve deeper into the philosophical aspects of physics. Einstein's Nobel Prize in 1921 also came at a time when he was gaining increasing recognition, not just as a scientist, but also as a public figure. As his fame grew, he became a vocal advocate for peace and social justice, using his platform to speak out on a variety of issues. He was particularly outspoken against militarism, nationalism, and the growing threat of fascism in Europe. As the political climate in Germany grew more hostile under Adolf Hitler's rise to power in the early 1930s, Einstein became an outspoken critic of the Nazi regime. His strong anti-nationalist stance and his Jewish heritage made him a target for Nazi propaganda, and his books were among those burned by the regime. In 1933, Einstein was visiting the United States when Adolf Hitler came to power. Recognizing the danger of remaining in Germany, Einstein decided not to return and instead accepted a position at the Institute for Advanced Study in Princeton, New Jersey. This marked the beginning of his long residency in the United States, where he became an American citizen in 1940. His decision to leave Germany was not just driven by the rise of Nazism, but also by the growing political and intellectual climate that stifled free thought in the country. His move to America marked a pivotal moment in his life, as he would continue his work in physics and become deeply involved in various political causes, especially those related to civil rights and the fate of the Jewish people. While living in the United States, Einstein continued his work on theoretical physics and began to focus on problems related to the unification of the fundamental forces of nature. He spent the last decades of his life searching for a unified field theory, a single theory that would reconcile the forces of gravity and electromagnetism, the two fundamental forces that he had described in his earlier work. Though he never completed the theory and it remains an open problem in physics, his pursuit of a unified theory was a testament to his deep commitment to understanding the underlying laws of nature. In addition to his scientific work, Einstein became increasingly involved in political and social issues in the United States. He was a vocal advocate for civil rights, speaking out against racial segregation and the oppression of African Americans. Despite his fame, he was an outspoken critic of racism, and in his later years he joined the NAACP, National Association for the Advancement of Colored People. Einstein formed a friendship with African American civil rights activist W.L.B. Du Bois, and he was deeply moved by the struggles faced by Black Americans. Einstein was also a pacifist during much of his life, particularly after the horrors of World War I. However, with the rise of fascism and the growing threat of Nazi Germany, Einstein reconsidered his pacifist stance. In 1939, he signed a letter to President Franklin D. Roosevelt warning that Germany might be developing an atomic bomb and urging the U.S. to initiate its own nuclear research. This letter led to the establishment of the Manhattan Project, which ultimately resulted in the development of the atomic bomb. Einstein was later conflicted about the use of nuclear weapons, especially after the bombings of Hiroshima and Nagasaki in 1945. In his later years, Einstein's focus was split between his scientific endeavors and his work as a public intellectual. He continued to advocate for peace and for the peaceful use of atomic energy, calling for international cooperation to prevent further nuclear warfare. His legacy as both a scientist and a moral leader is enduring, and his thoughts on the intersection of science, politics, and society continue to influence discussions in both fields. Einstein's life was not just about equations and theories, but also about his commitment to human rights, intellectual freedom, and social justice. His voice was a powerful one in the 20th century, and his impact on both science and society remains as relevant today as it was during his lifetime. After leaving Germany in 1933 due to the rise of Adolf Hitler and the Nazi regime, Einstein moved to the United States, where he would live for the remainder of his life. He accepted a position at the Institute for Advanced Study in Princeton, New Jersey, a place that would become his intellectual home for nearly 2 decades. This marked a significant turning point in his life. Despite his initial plans to return to Europe after the fall of the Nazi regime, the increasing political instability in Europe, combined with his growing concerns over the political climate in the U.S., led him to stay in America permanently. His emigration was not solely due to the political situation in Germany, it was also driven by his desire for intellectual freedom and the opportunity to continue his work on new areas of theoretical physics. In the United States, Einstein became a U.S. citizen in 1940, making him not only a public figure in the world of science, but also a prominent political activist. He was deeply involved in advocating for civil rights, speaking out against racial discrimination, and supporting the efforts of African American leaders during the civil rights movement. Despite his fame, Einstein was acutely aware of the inequality and racism prevalent in the U.S., particularly in the South, and he was unapologetically outspoken about it. He formed a notable friendship with W.E.B. Du Bois, the prominent African-American civil rights leader, and expressed his concerns regarding the segregation and disenfranchisement of Black Americans. Einstein's engagement with social and political issues extended far beyond racial justice. His pacifist leanings, rooted in his personal experiences during World War I, were tested once again as the threat of World War II loomed large. In the years leading up to the war, Einstein was outspoken in his belief in peace and diplomacy. However, as Nazi Germany began to push forward its agenda, Einstein became increasingly concerned with the possibility of a Nazi atomic bomb and the need for the United States to develop its own nuclear weapons in response. In 1939, Einstein co-signed a letter to President Franklin D. Roosevelt, warning of the Nazi regime's potential interest in building an atomic bomb and urging the U.S. to begin its own research. This letter eventually contributed to the creation of the Manhattan Project, which would develop the first nuclear weapons. Einstein himself was not directly involved in the project, but he later expressed regret over the use of nuclear weapons against Japan, especially after the bombings of Hiroshima and Nagasaki in 1945. His letter had, in a sense, helped make the destructive potential of nuclear energy a reality, something that haunted him for the rest of his life. Despite his initial pacifist views, Einstein became more politically involved in the post-war era, advocating for global peace and the peaceful use of nuclear energy. After the war, he advocated for international cooperation, calling for a world government that would help prevent the recurrence of global conflict. Einstein also worked tirelessly to promote human rights and was vocal in his support for Jewish causes, particularly in the wake of the Holocaust. During his years in the U.S., Einstein's work continued to revolve around fundamental questions in physics, particularly his search for a unified field theory. His hope was to find a single, elegant theory that would unite the forces of gravity and electromagnetism. Though he was never able to complete this theory, his work on the subject led him to further explore the connections between different forces in nature, laying the groundwork for future physicists to build upon. His later years were marked by a sense of both intellectual fulfillment and personal sadness. Despite his achievements in physics, Einstein's personal life was not without turmoil. His first marriage to Maelva Marek, a fellow physics student, ended in divorce in 1919. They had 2 sons together, Hans Albert and Eduard, but their marriage struggled due to Einstein's intense dedication to his work and his demanding career. His second marriage to his cousin Elsa Lowenthal was more stable, but Elsa's health problems and Einstein's deep focus on his scientific endeavors created tensions in their relationship as well. Einstein's focus on finding a unified theory occupied much of his later life, but he was also keenly interested in the philosophical implications of his work. Throughout his career, Einstein sought to reconcile his scientific insights with his philosophical and spiritual beliefs. He famously said that his view of the universe was akin to a cosmic religion, and that he saw God not as a personal deity, but as the embodiment of the laws of nature. He was often critical of organized religion, particularly its dogmatic aspects, but he believed that the sense of awe and wonder that comes with the study of the natural world could inspire a deep, almost spiritual respect for the universe. Despite his fame, Einstein retained a humility about his work, often attributing his success to his ability to look at problems from new and unconventional perspectives. He believed that scientific progress was not only about discovering new facts, but also about expanding the way humans thought about the universe. His own intellectual journey was deeply shaped by curiosity, imagination, and a willingness to challenge the status quo, qualities that defined his character both as a scientist and as a person. Einstein also spoke extensively on matters related to politics and ethics. He warned against the dangers of totalitarianism and called for democracy and the preservation of individual freedoms. In a few minutes, his life seemed to be constructed around his values, career, and his passion. His political views often aligned with his belief in intellectual freedom, the necessity of social justice, and the importance of rational discourse in solving the world's problems. His critique of nationalism, especially in the context of both World War I and World War II, underlined his belief in international cooperation and peace as essential for the survival of humanity. In his later years, Einstein's fame as a scientist had made him a global icon, and his thoughts on a wide range of topics, ranging from science to ethics to politics, were widely read and influential. He used his platform to speak out on issues such as the dangers of nuclear weapons, the importance of education, and the need for a more peaceful and just world. His ideas, while deeply rooted in the scientific method, were never just about advancing knowledge for its own sake. They were always intertwined with his larger concerns about humanity's future. Einstein passed away on April 18, 1955, at the age of 76 in Princeton, New Jersey, leaving behind. His contributions to physics have had a lasting impact, and his work continues to shape our understanding of the universe. His theories of relativity, as well as his work on quantum mechanics, continue to inform and inspire physicists to this day. But Einstein's influence extended far beyond the realm of science. His commitment to peace, his advocacy for civil rights, and his philosophical reflections on the nature of reality and the human condition have cemented his place as one of the most influential intellectuals of the 20th century. Einstein's legacy lives on in the continued exploration of the cosmos, the application of his theories in modern technology, and in the enduring value of curiosity, creativity, and intellectual freedom. He remains a symbol of the power of scientific inquiry and the belief that through reason and compassion, humanity can create a better future. Albert Einstein's influence extends far beyond his groundbreaking contributions to theoretical physics. While his theories of special relativity and general relativity revolutionized our understanding of space, time, and gravity, Einstein's impact also stretched into the realms of philosophy, ethics, politics, and global humanism. His profound legacy includes not only the scientific advances that transformed the 20th century, but also his moral compass and commitment to a better world, especially in times of crisis. Einstein's approach to science was grounded in a profound sense of curiosity and imagination, which drove him to question established scientific theories and push the boundaries of knowledge. His early work, which included the photoelectric effect, for which he was awarded the Nobel Prize, laid the foundation for much of modern quantum mechanics. His equation, E=mc2, which expresses the equivalence of mass and energy, revealed the immense power locked in even the smallest amount of matter and contributed to the development of technology such as nuclear energy, though Einstein himself was conflicted about its military use after the devastation of Hiroshima and Nagasaki. Einstein's work on general relativity, however, was arguably the most profound of all. It redefined our understanding of gravity, not as a force between objects, but as the curvature of space-time caused by mass and energy. The famous prediction of the bending of light by gravity, which was confirmed in 1919 by British astronomers, propelled him to international fame. General relativity also led to the prediction and later observation of phenomena like black holes and gravitational waves, concepts that would not be fully understood or confirmed until decades later. These contributions laid the groundwork for much of modern cosmology and astrophysics, and his ideas continue to guide research in these fields today. However, Einstein's scientific pursuits were not divorced from his concerns about humanity. As an outspoken critic of militarism, nationalism, and the growing threat of fascism in Europe, Einstein's personal life was marked by a commitment to intellectual freedom, social justice, and peace. Having experienced firsthand the horrors of war and anti-Semitism, Einstein believed that knowledge should be used for the betterment of mankind, not for the advancement of destruction. In the face of rising Nazism and the persecution of Jews, Einstein, who was a German Jew, felt increasingly vulnerable. In 1933, when Adolf Hitler came to power, Einstein was visiting the United States and made the decision not to return to Germany. He accepted a position at the Institute for Advanced Study in Princeton, where he would spend the remainder of his life. This move came at a time when European Jews were facing escalating discrimination and violence. His decision to remain in the U.S. was not only a personal one, but was driven by his growing awareness of the dangers of fascism and his belief in the safety and intellectual freedom that the U.S. provided. Although Einstein had initially been a staunch pacifist, he reconsidered his stance when he learned that Nazi scientists were attempting to build an atomic bomb. In 1939, he co-signed a letter with physicist Leo Szilard, warning President Franklin D. Roosevelt about the possibility of a German atomic bomb. This letter played a crucial role in the initiation of the Manhattan Project, which would eventually lead to the development of the first nuclear weapons. However, Einstein's role in the project was indirect, and he later expressed deep regret over the use of atomic bombs on Hiroshima and Nagasaki, fearing that the bomb could lead to an arms race that might bring about the destruction of civilization. Despite the shift in his views during World War II, Einstein's ultimate commitment to peace and his warnings about the dangers of nuclear weapons were constant. After the war, he became a staunch advocate for internationalism, advocating for the creation of a world government to ensure peace and prevent future conflicts. He was a vocal supporter of the United Nations and hoped that international cooperation would lead to lasting peace. In his later years, he famously said, "We shall require a substantially new manner of thinking if mankind is to survive." Einstein's intellectual and ethical concerns extended to other aspects of society as well. His engagement with civil rights in the United States made him a prominent voice in the fight against racism and inequality. He became an outspoken critic of segregation, especially in the American South, and was an active supporter of African American civil rights. His friendship with figures like W.E.B. Du Bois and his public statements against racial discrimination in America highlight his commitment to justice on a global scale. Einstein was also an ardent critic of McCarthyism during the early Cold War period. The Red Scare and the growing climate of fear and repression in the U.S. deeply troubled him. He believed in the protection of intellectual freedom and spoke out against the government's tactics of silencing and persecuting political dissent. His support for individuals who were persecuted for their political beliefs and his advocacy for freedom of thought made him an important figure in American intellectual life. Though Einstein was primarily known for his work in physics, his philosophical beliefs also had a significant impact on the way people thought about science and life. Einstein was often asked about his religious views, and he consistently expressed a belief in a cosmic religion that embraced the awe and mystery of the universe, but he did not believe in a personal anthropomorphic God. He saw science as a means to understand the natural laws of the universe and believed that the pursuit of knowledge was a noble endeavor. Einstein was highly skeptical of organized religion and rejected traditional dogma, but he respected the moral and ethical teachings that many religions offered, especially in terms of compassion and justice. He once famously said, "The most incomprehensible thing about the world is that it is comprehensible." Einstein's ability to reconcile the rational and the mystical, his scientific discoveries alongside his deep sense of wonder about the universe, gave his life and work a sense of wholeness that continues to inspire people across disciplines. His dedication to truth-seeking, ethical responsibility, and human progress made him not just a scientist, but a moral figure whose impact stretched across generations. Einstein's later years also saw him engage deeply with the question of human potential. He believed that education was the key to unlocking human progress and improving society. His ideas on education were influenced by his own experiences as a student and his frustration with the rigid structures of formal schooling. He believed that true education nurtured creativity, curiosity, and a spirit of inquiry rather than rote memorization. This belief was evident in his support for various progressive educational initiatives and his role as a mentor to many younger scientists and thinkers. Albert Einstein died on April 18, 1955 from an abdominal aneurysm at the age of 76. In his death, he left behind a legacy that transcended his scientific achievements. His theories continue to influence the fields of physics and cosmology, but his commitment to social justice, civil rights, internationalism, and peace also marks him as a visionary who used his intellect for the betterment of humanity. He remains a global symbol of intellectual curiosity, the pursuit of truth, and the ethical responsibility that comes with scientific knowledge. Einstein's enduring impact on modern science, philosophy, politics, and culture speaks to the depth of his genius and the breadth of his vision. His work laid the foundation for future scientific advancements, including the discovery of gravitational waves, the study of black holes, and ongoing research into quantum mechanics. His ethical stance and commitment to justice continue to inspire activists and leaders fighting for human rights, peace, and social change. Even decades after his death, Einstein's name remains synonymous with innovation, intellect, and a belief that the pursuit of knowledge can change the world for the better. Before diving into the famous equation E = mc², let's first explore the mind behind it. This simple yet revolutionary formula was proposed by Albert Einstein, and it fundamentally changed the way we view the universe. E = mc² is one of Albert Einstein's most famous formulas, introduced in his special theory of relativity. It explains the relationship between energy and mass, m, showing that they are interchangeable. E = energy, m = mass, c = speed of light. In a vacuum, which is approximately 2,997,92458 meters per second, Einstein's equation E = mc², opened up a new understanding of the fundamental nature of matter and energy. It suggests that mass and energy are not two distinct things, but two expressions of the same underlying concept. This insight transforms how we think about the universe and its underlying processes, showing that mass is just a concentrated form of energy. Before Einstein's groundbreaking work, mass and energy were considered separate. Energy was something you could apply to move objects or heat things, and mass was something tangible and measurable. However, this formula linked the two in a direct way, revealing that they are essentially interchangeable. The importance of this equation lies in its suggestion that mass can be converted into energy and vice versa. The idea that mass can be turned into energy seems counterintuitive because we tend to think of mass as something stable and fixed. But when you consider the universe's extreme environments, like the inside of stars or the vast explosions of supernovae, this concept becomes crucial. In these intense environments, a small amount of mass is converted into an immense amount of energy. leading to the vast radiations and heat we observe. The most familiar example of this transformation is in nuclear reactions. In these reactions, atoms are split or fused, and their mass is converted into energy, which is released in the form of radiation and heat. This principle is not just theoretical, it's what powers the sun, where nuclear fusion converts a tiny fraction of mass into vast quantities of energy. Another significant consequence of the equation is its ability to explain how energy can be stored in matter. Even everyday objects, which seem solid and unchanging, contain massive amounts of energy locked within their mass. This realization has profound implications for how we think about energy sources. For instance, in nuclear energy, atoms are manipulated to release this stored energy, which is far more efficient than conventional chemical reactions like burning coal or oil. The ability to release such massive amounts of energy from relatively small amounts of matter has led to the development of nuclear energy as a powerful and sometimes controversial source of energy. At a cosmic scale, this equation plays a crucial role in understanding how the universe operates. It explains the process by which stars, like our sun, generate energy. The sun's fusion process involves the conversion of hydrogen atoms into helium, and even though the mass lost in the process is minuscule, it translates into enormous energy release. Without this mass-to-energy conversion, stars would not be able to shine for billions of years, and life on Earth would not be possible. Similarly, when we look at black holes or other extreme gravitational phenomena, Einstein's equation helps us understand how mass and energy interact in environments with intense gravity. The bending of space-time around massive objects is another manifestation of how mass and energy are linked. The equation also influenced new areas of theoretical physics, such as quantum mechanics, where understanding the relationship between energy and matter on the smallest scales is crucial. The discovery of quantum tunneling, where particles can move through barriers that seem impenetrable in classical physics, was made possible by insights derived from E=mc2 dot. It is also instrumental in our understanding of the universe's origins, particularly the energy released in the Big Bang, and how matter evolved from the energy of the early universe. It guides physicists in their ongoing search for a unified theory that could explain all the forces of nature. In a more practical sense, E=mc2 has reshaped technology. Modern technologies like positron emission tomography, PET, scans in medical imaging, or the creation of energy in nuclear reactors depend on the relationship between mass and energy. These technologies, derived from Einstein's work, have revolutionized fields from medicine to energy production, improving lives in ways he could hardly have imagined. The use of nuclear energy in particular has become central to discussions about sustainable energy, as it holds the potential to generate large amounts of electricity from relatively small amounts of fuel. Einstein's equation has also had philosophical implications. It challenges our perceptions of the physical world, inviting us to reconsider what we know about the structure of matter. The idea that energy can be both stored in mass and released by it prompts us to rethink the very nature of the universe and our place in it. It shows how something as common as matter, which we experience daily in tangible, solid forms, is deeply connected to the forces that govern the cosmos. It also underscores the profound interconnectedness of all physical phenomena, from the atomic scale to the grand workings of galaxies and stars. In essence, E=mc2 is more than just an equation in physics. It is a reminder that the world around us is far more dynamic and interconnected than we can often see or understand. Through this formula, Einstein revealed a universe in which matter and energy are intimately connected, shaping everything from the tiniest particle to the largest cosmic structures. It teaches us that energy is not something external we apply to matter, but something that is inherent in matter itself. This realization has reshaped how we view nature and has driven scientific advancements that continue to transform our world. Einstein's equation, E equals mc2, represents one of the most revolutionary ideas in the history of physics. This deceptively simple formula expresses the deep and fundamental connection between mass and energy. It suggests that mass, which we typically consider a measure of the amount of matter in an object, is not a fixed and immutable property. Instead, mass is simply a form of energy stored in a particular way, and under the right conditions, it can be released as energy. This insight opened the door to new ways of thinking about how the universe operates, from the atomic level to the scale of stars and galaxies. The relationship between mass and energy is more than just theoretical. It plays out in the real world in profound ways. For instance, the energy that powers everything from light bulbs to nuclear reactors and even the explosion of stars is all tied to this principle. When Einstein introduced E equals mc2, he was showing that mass is not just the weight of an object, it is a reservoir of energy waiting to be tapped into. This led to a better understanding of how nuclear energy works. In nuclear reactions, such as the process of fission, splitting atoms, or fusion, combining atoms, a small amount of mass is lost, but this loss results in a large amount of energy being released, in accordance with the equation. The process of nuclear fission, which powers nuclear reactors and atomic bombs, illustrates this principle in action. The equation also has applications in understanding stellar energy production, such as how the sun shines. The sun's energy is generated by nuclear fusion, where hydrogen atoms are fused together to form helium. During this process, some of the mass of the hydrogen atoms is converted into energy in the form of light and heat. This energy is what powers the sun and sustains life on Earth. E equals mc2 explains the sun's ability to produce so much energy from relatively small amounts of matter. Essentially, how a star like the sun can burn for billions of years. Without this equation, we wouldn't understand the incredible efficiency of stars in converting mass into energy. On a larger scale, E equals mc2 also plays a key role in understanding the behavior of black holes and other extreme astrophysical objects. In the intense gravitational fields near black holes, mass can be converted into energy in unusual ways, leading to phenomena like gravitational waves and the emission of high-energy radiation. The enormous gravitational forces near a black hole are capable of bending the very fabric of space-time itself, causing the release of vast amounts of energy as matter falls in and is ultimately crushed into singularities. Einstein's theory also helped us realize that the entire cosmic microwave background radiation, which provides evidence for the Big Bang, is tied to the energy produced in the early universe, when matter and energy were more closely linked. At the atomic level, E equals mc2 explains why particles like electrons, protons, and neutrons behave the way they do. The energy stored in these particles comes from their mass, and that energy can be released under certain conditions. For example, in particle accelerators, scientists use powerful machines to accelerate particles to nearly the speed of light, thus increasing their energy. As these particles collide, some of their energy is transformed into new particles, and this transformation is governed by the relationship between mass and energy that E equals mc2 defines. Moreover, this equation has deeply impacted how we think about the conservation of energy and conservation of mass. Prior to Einstein, physicists believed in the separate conservation of mass and energy in different contexts. However, with E equals mc2, the understanding of conservation evolved. It became clear that mass and energy are interchangeable, and in any process, whether it's chemical reactions, nuclear reactions, or the workings of the cosmos, the total amount of mass and energy remains constant, but the forms in which they exist can change. For example, in a chemical reaction, the mass might appear to remain constant, but tiny amounts of mass can be converted into heat and light. which is energy. This understanding has deepened our knowledge of how physical processes work, from the subatomic to the macroscopic scale. The implications of this formula go beyond physics into other fields, influencing technology, medicine, and even our understanding of the future. The relationship between energy and mass, explained by E equals mc2, is integral to the functioning of nuclear medicine. In medical imaging techniques like positron emission tomography, PET, particles with mass are used to detect and treat diseases like cancer by using the energy released during the annihilation of particles. These applications, derived from Einstein's theory, have become vital tools in modern healthcare. On the technological front, the equation has driven innovations in nuclear energy. Opportunity for sequencing, what it is, an innovation. Power plants harness the ability to convert small amounts of nuclear fuel into large amounts of electricity by utilizing the mass-energy relationship. Similarly, the development of nuclear weapons relied on the ability to release energy by converting mass into energy at an extremely high rate. The same equation that powers nuclear reactors also explains the destructive force of atomic bombs. In the long run, the equation's role in nuclear energy has raised important ethical and environmental discussions, particularly regarding how to handle nuclear waste, safety, and the potential for misuse. In a broader philosophical sense, E equals mc2 challenges the way we think about the material world. It tells us that everything we see around us, including ourselves, is made up of tiny particles that not only have mass, but also store immense amount of energy. This equation changes the way we look at life, the universe, and our place in it. It reinforces the idea that the laws of nature operate on a much deeper level than our everyday experiences suggest. It shows us that even the most solid, tangible objects are just forms of concentrated energy, constantly in motion, constantly in flux. Einstein's equation also holds significant implications for the future. As we continue to explore the frontiers of science, E equals mc2 will likely play a central role in unlocking new energy sources, understanding dark matter and dark energy, and advancing technologies like quantum computing and space travel. It offers a fundamental insight into the interconnectedness of all physical phenomena, which may guide future generations of scientists to explore new ways of harnessing energy, manipulating matter, and understanding the universe at ever deeper levels. At the core, E equals mc2 represents more than just a formula. It embodies a revolutionary shift in our understanding of the universe. It links mass and energy in a way that had never been considered before, showing that the universe is far more interconnected and dynamic than we ever imagined. This relationship between mass and energy forms the basis for everything from the smallest particles to the largest galaxies, and from the atomic age to the future of space exploration. Einstein's insight into this deep connection between matter and energy continues to shape the path of scientific inquiry and technological development. Albert Einstein's equation, E equals mc2, is not just a formula in physics. It represents a fundamental shift in how we understand the fabric of the universe. It goes beyond simple math and offers profound insights into the very nature of reality. When Einstein proposed that mass and energy are interchangeable, it meant that the seemingly solid objects around us, including ourselves, are just different manifestations of energy. This breakthrough connected the physical world to the core principles of energy and matter, transforming science and offering new pathways to understanding the universe. At the heart of the equation is the idea that energy and mass are two sides of the same coin. Energy is often thought of as something that powers machines or heats homes, while mass is something tangible, a measure of an object's matter. Einstein's theory, however, showed that mass itself is a form of energy stored within objects in a concentrated way. The formula E equals mc2 is a mathematical representation of this concept. A small amount of mass, when converted, can produce an enormous amount of energy because of the speed of light, which is squared in the equation. The speed of light is an enormous number, so C2 makes the energy released from even a tiny amount of mass incredibly powerful. This insight has vast implications for both theoretical and applied physics. For instance, in the world of nuclear physics, E equals mc2 is used to understand nuclear reactions, where small changes in mass result in large releases of energy. In nuclear power plants, atoms like uranium are split through fission, releasing energy as a result of the mass lost in the process. Similarly, the fusion process, which powers stars, involves the combination of light atoms like hydrogen to form heavier atoms like helium, again releasing energy. E equals mc2 shows that energy is not a separate entity, but rather an intrinsic part of the mass of atoms and particles. This equation allows us to comprehend why stars shine. They convert a portion of their mass into the vast amounts of energy that radiate out as light and heat. The importance of this equation reaches far beyond the Earth and into the cosmos. When we observe the behavior of celestial bodies like black holes, supernovae, and neutron stars, we see mass and energy interacting in extreme conditions. In the case of black holes, for instance, the immense gravitational pull of these objects causes them to warp space-time, resulting in dramatic changes in how mass and energy behave near their event horizon. The mass of a black hole bends the fabric of space-time so severely that not even light can escape. The energy released in these interactions is linked to the mass of the object, and understanding the relationship between the two is critical to unlocking the mysteries of the universe's most extreme phenomena. The theory also has crucial implications in cosmology, particularly in the context of the Big Bang theory. E equals mc2 helps explain how the universe began as an incredibly dense and hot mass of energy. In the early moments after the Big Bang, the universe was so hot that particles could not exist in the usual forms of matter. As the universe cooled, energy began to condense into mass, forming atoms, stars, and galaxies. The equation shows that the universe started as pure energy, and as it cooled, that energy was converted into the mass that eventually formed the structures we see today. By understanding the connection between mass and energy, we can trace the origin and evolution of the universe itself, observing how the energy released in the Big Bang eventually became the matter that makes up everything we know. In practical terms, E equals mc2 has also led to numerous technological advancements. The most obvious of these is the development of nuclear energy, where mass is intentionally converted into energy to power cities, factories, and homes. The advent of nuclear weapons also relies on this same principle, although it is the destructive potential of mass energy conversion that has raised significant ethical and moral questions. While the equation offers a clean and efficient energy source, it also poses risks, particularly in terms of radioactive waste and the potential for devastating consequences in the wrong hands. These ethical concerns around nuclear energy continue to shape global conversations on energy production, environmental sustainability, and geopolitics. Beyond energy, E equals mc2 has been instrumental in other fields as well, particularly in medicine. Technologies like positron emission tomography, PET scans, rely on principles that are rooted in Einstein's equation. PET scans allow doctors to detect diseases like cancer by tracking the energy released during the annihilation of particles. In these scans, tiny amounts of radioactive material are introduced into the body, and as particles decay, their mass is converted into energy, which is detected by the scanner. This principle has made a huge impact on healthcare by providing non-invasive ways to look inside the body and detect abnormalities in organs or tissues before they become life-threatening. The equation also influenced quantum mechanics and the theory of relativity, forming a bridge between these two areas of physics. In quantum mechanics, the behavior of particles at the smallest scales is influenced by their mass-energy relationship, the famous Heisenberg uncertainty principle, which asserts that certain pairs of physical properties, like position and momentum, cannot be simultaneously known to an exact degree, has its roots in the uncertainty surrounding mass-energy interactions at quantum scales. Wow. Similarly, in general relativity, mass and energy shape the curvature of space-time, affecting everything from the orbit of planets to the path of light in gravitational fields. Understanding these interactions through E=mc2 has led to breakthroughs in technology like GPS, where satellites account for the effects of relativity in their positioning systems. Looking forward, the relationship between mass and energy may hold the key to future scientific and technological breakthroughs. E=mc2 suggests that unlocking energy from mass could lead to revolutionary energy sources, potentially helping to solve some of the world's energy problems. For example, the development of fusion reactors that replicate the process by which stars generate energy is an ongoing effort to harness the mass energy conversion process on Earth. If successful, this could provide virtually limitless free energy. Similarly, breakthroughs in particle physics and quantum computing may be influenced by the mass-energy principle, leading to innovations we can only begin to imagine. In the field of space exploration, understanding E=mc2 allows us to consider the vast distances between stars and galaxies. As scientists continue to probe the nature of dark matter and dark energy, the principles embedded in Einstein's equation will likely play a crucial role in uncovering new mysteries of the cosmos. If we ever manage to travel to distant stars or other galaxies, understanding the relationship between mass and energy will be fundamental in developing the technologies necessary for such long-distance travel. Ultimately, E=mc2 represents more than just a formula for converting mass into energy. It symbolizes a deeper understanding of the universe's fundamental nature, one in which matter and energy are interchangeable, interconnected, and constantly at play. Through this simple yet profound equation, Einstein forever changed how we view the universe, offering a new perspective on everything, from the creation of the cosmos to the behavior of subatomic particles to the future of technology. It has become a cornerstone of modern science, influencing not just physics, but nearly every field of inquiry and innovation. Einstein's equation E=mc2 is one of the most profound and transformative concepts in modern physics, with implications that stretch far beyond the realm of theoretical science. This formula expresses the relationship between mass, energy, E, with the C2 representing the square of the speed of light in a vacuum, a constant that serves as a conversion factor between mass and energy. At its core, this equation suggests that mass and energy are not two separate entities, but rather two interchangeable forms of the same thing. While mass is typically considered a measure of the amount of matter in an object, E=mc2 shows that mass is simply a form of energy, which can be converted into other forms, and vice versa. This insight into the nature of mass and energy led to a radical shift in how we understand the physical world. Before Einstein, scientists generally treated mass and energy as distinct concepts. Energy, for example, was typically thought of as something that could be harnessed to do work, like the energy used to power machines, heat homes, or fuel chemical reactions. Mass, on the other hand, was seen as a fixed property of matter, a measure of how much stuff an object contain. But E equals mc2 revealed that the two are intimately connected and can be converted into each other under the right conditions. A key takeaway from this formula is that even a small amount of mass contains an enormous amount of energy. The speed of light, f, is a very large number, roughly 300,000 kilometers per second. And when squared, it becomes an even larger value. This means that even tiny particles, like atoms or subatomic particles, contain vast amounts of energy. In practical terms, this principle is most evident in nuclear reactions. In both nuclear fission, the splitting of atomic nuclei, and nuclear fusion, the combining of atomic nuclei, small amounts of mass are converted into large amounts of energy. In nuclear power plants, the process of fission releases energy as uranium or other heavy elements are split, and this energy can be harnessed to produce electricity. In the sun, fusion reactions occur at the core, where hydrogen atoms are fused into helium, and a small portion of the mass is lost as energy, which is then radiated outward as light and heat. The understanding that mass and energy are interchangeable also explains the energy produced in nuclear weapons. When a small amount of mass is converted into energy in an uncontrolled chain reaction, the result is an explosive release of energy. While the destructive power of nuclear weapons is clear, this principle also powers the peaceful use of nuclear energy, where carefully controlled reactions release energy to generate electricity. Einstein's equation also has profound implications for our understanding of the universe, particularly in astrophysics and cosmology. In black holes, for example, the immense gravitational pull bends the fabric of space-time and causes matter to collapse into a singularity, where mass is crushed into an infinitely small point. The conversion of mass to energy in these extreme environments creates phenomena like gravitational waves and the release of high-energy radiation, both of which have been studied by astronomers and physicists. Similarly, the process by which stars shine, by converting mass into energy through fusion, further underscores the deep connection between mass and energy. E equals mc2 helps explain the life cycle of stars, from their formation to their death, whether as a white dwarf, a neutron star, or a black hole. The broader implications of E equals mc2 have been crucial in other scientific fields as well. In quantum mechanics, the equation highlights the relationship between energy and the particles that make up the universe, helping to explain phenomena like quantum tunneling and the behavior of subatomic particles. In general relativity, mass and energy influence the curvature of space-time, causing the gravitational effects we observe, such as the orbits of planets around stars and the bending of light around massive objects like galaxies and black holes. The formula's impact is also evident in practical technologies that have transformed our daily lives. For instance, positron emission tomography, PET, scans in medical imaging rely on the principles of mass-energy conversion. In PET scans, radioactive isotopes are injected into the body, and as these isotopes decay, they release energy in the form of gamma rays. These emissions are then detected to create detailed images of the body's internal structures, allowing doctors to diagnose diseases such as cancer with greater precision. Furthermore, E equals mc2 has paved the way for future scientific advances. In fusion energy research, scientists are trying to replicate the fusion processes that occur in stars, where mass is converted into energy. If successful, fusion energy could provide a nearly limitless and clean source of power, potentially revolutionizing the energy landscape of the future. Ultimately, Einstein's equation is more than just a mathematical expression. It's a window into understanding the deepest workings of the universe. By revealing the fundamental equivalence of mass and energy, E equals MC2 has reshaped our understanding of everything from atomic reactions to cosmic phenomena. It has led to technological advancements, shaped our understanding of the cosmos, and continues to drive scientific discovery today. As we explore new frontiers in physics and technology, this equation remains one of the cornerstones of modern science, demonstrating how interconnected the forces of nature truly are. Albert Einstein's equation, E equals mc2, is far more than just a formula. It is a profound revelation about the very fabric of our universe. By showing that mass and energy are interchangeable, it has reshaped our understanding of everything from the tiniest particles to the vastness of space. It has opened doors to groundbreaking discoveries in physics, revolutionized energy production, and even impacted fields like medicine and space exploration. The beauty of this equation lies in its simplicity and elegance. Yet the depth of its implications continues to influence science, technology, and philosophy to this day. As we continue to explore the mysteries of the cosmos, tackle global challenges, and innovate for the future, E equals mc2 will remain a guiding principle, reminding us that the universe operates in interconnected ways that we are only beginning to fully understand. So, in a world that constantly evolves, Einstein's insight will continue to inspire generations to come, challenging us to think differently, to question the unknown, and to embrace the endless possibilities that lie within the energy of matter itself. Thank you.